Hi, everybody. My name is Alex Rosenthal, and welcome to the Garbage In, Knowledge Out webinar presented by Ivan Miletic. Thank you all very much for joining us. This is the fourth presentation in our In Control webinar series, and we're very happy to see several familiar names in attendance, as well as some new attendees. For those of you who have attended our previous webinars, this one will be just a little bit different. And that's mainly because Ivan's expertise is a bit different than many process engineers working in the water resource recovery sector. Ivan is our data analytics leader, and he has over 20 years of experience in modeling, control, and optimization of complex systems. And his experience has been in many industries, including steelmaking, food processing, fuels, pharmaceuticals, and for the past several years, water resource recovery. Ivan joined In Control Solutions in 2016, and since then he has contributed greatly to the development of tools for sensor and process fault detection, data-driven modeling, and process optimization. As I alluded to earlier, Ivan's approach to engineering problems is rather distinct from the approaches that many of us process engineers are accustomed to. And for that reason, both our CEO, Liv Rieger, and our CTO, Oliver Schra, will be jumping in at various times during Ivan's presentation to add their process engineering perspective to complement Ivan's data analytics methods. So without further ado, I'm very happy to turn things over to our friend and colleague, Ivan Miletic.
Okay, thanks, Alex. We're going to discuss today some applications of data analytics methods and how they can be used for wastewater treatment plants and bioprocesses in general, I hope. We're going to show you some results on these two cases, basically how you can do some practical data cleaning and data conditioning based on some time series modeling. That's in case one, and then how you can use data-driven modeling as a means to for process improvement. In this case, sludge dewatering. Okay. So the cases are going to be discussed or focused around two data-driven modeling methods. Basically, time-based correlations that look at a time series of data and how that time series can be used to generate some useful information, specifically for sensor drift and things like this. And then multivariate methods, basically how variables relate to each other in a process and how this can be modeled and then used to some advantage for process improvement. Okay, and like I said, we're going to look at two case studies, and then what I'm hoping is that you'll notice that there's maybe a common theme throughout the slides is that we're looking at data-driven methods and how they can be used by themselves, but also to complement other modeling techniques that you may be familiar with. Okay. All right. So where do you begin with this kind of a talk? So you might think of then data requirements. If we're going to talk about data, we have to know what data are needed for a particular piece of work or for a scope that needs to be delivered as part of a project. And when we're discussing these methods, we realize that data requirements are going to be generally speaking project specific or specific to operational needs and requirements of a plant. All right, and we also recognize that the data sources that may be available or that need to be developed for providing the information that we need, they need to be kind of assembled and put together, and that this is not always an easy thing to do. It's often a messy thing. All right. So the title it has the words garbage in it. So why do we choose to say that? It's we're looking at here basically as a recognition that the idea of assembling a data set, putting a data set together, and then extracting information from that data set is not always easy. In fact, I would say that a large part of the effort in any modeling or engineering work that you might typically encounter faces some typical problems regarding assembling of a data set. I personally have not run into any data set that's been perfectly conditioned. Always there's something that needs to be adjusted before you can do some kind of modeling or develop any kind of inference based on the data set. Data are typically unsynchronized. The variable observations don't match up with each other. There are gaps and inconsistencies. And then various sources are sampled at different rates. They all have to be put together. So you may rely on spreadsheet data dumps and these sorts of mechanisms for acquiring data and then working with them. But I would suggest that maybe this is not the optimal way of doing that, and that doing something a little bit more systematic than that would be better. So this is just a general comment from me regarding saving time and being able to work with the data set. Okay, so what does this look like in general? What do you see in a data set? At least this is my experience with wastewater data. So and data from other types of plants, like say bioreactors and these sorts of data sources. So you might see a data set like this. This I think we looked at maybe about a year or two that this data set came through our offices. We work with this. The first thing you should notice is that the timestamps are out of order. They're not matched up. Variables are presented in a spreadsheet form with jumbled rows. They need to be reconciled and adjusted. Gaps and inconsistent values need to be worked with. Some values are measured regularly, others are not. And then there's inconsistencies and outliers, and it's often difficult even to tell what is a measured value and what is not. Okay, so we're suggesting that a database or a database-centered approach to managing data may be easier than dealing with this with spreadsheets, especially if you want to import your data in whatever state they're in and then process them in a systematic way. Okay. So this idea of a systematic approach, we're showing you this flowchart, those blue boxes there for data storage through data processing, then into model development and output generation and that. We're showing you that as kind of a mental map as to how you may think about what you're doing with your data set. Now, I find this framework useful because it points to isolating and then recognizing that specific problems occur in the idea of assembling a data set and then extracting information from it. And for me, this applies to any kind of modeling that I've ever been involved in, whether it's mechanistic models, state space models, state estimators, various hybrid models, data-driven models. It doesn't matter from at least from my experience, and that this idea, these sets of general steps that are applied to data processing and data management always seem to apply. Okay, and what we're focusing on here is that data pre-processing step, and then the data model development. Basically, how do you create a useful model for a data-driven model? Then how do you run that model? How do you execute it? And then what do you do with the outputs? That's kind of the focus of this talk. Okay, but just keep this mental map in mind, and you may find it useful. All right, so this slide is kind of put in here to underline the idea that data and information are not the same thing. Okay, this may sound simple, but it's important to realize that Data are kind of a container that you should open up and extract information from. And the general steps for that include cleaning the data, conditioning the data, making sure the data are prepared and are ready for some kind of analysis that you may be interested in, whether that's modeling or just looking at some simple averages or anything really. But you need to do data cleaning and conditioning, outlier removal, these sorts of things, so that you can support decision analysis, the decision support. Okay. This information extraction, especially the data cleaning and adjustment, is part of every project that at least that I can think of that involves data. All right. So that suggests that if you're going to do data cleaning or data processing of some kind, that there's a question of tool selection. What are you going to use to do these tasks, or to perform these tasks? If you want to do outlier removal and say cleaning up or adjusting data that comes from a sensor you may think is faulty or it has a drift in it or something like that, what tools should you use to do that? So lots of tools exist, and I would suggest that simpler is generally better, but you don't want to make it so that it's too simple. Tools that are ad hoc approaches, like calculating out a mean or looking at pairwise correlations between variables, that can be useful, but only in a limited sense, at least in my opinion. So what I would suggest is that you kind of think about the methods that are on the right-hand side of this chart. Especially the PCA, PLS, maybe these neural network kind of ideas that look at correlations between variables explicitly and how variables work together to provide a certain process outcome. All right. So the methods that we're going to discuss today are going to be based on autocorrelation ideas, basically how a variable is related to its own past values. That is, if you think of a measured value and you take it at a certain point in time, how is that related to a measured value on the same variable that you took 1 hour ago or 2 days ago or something like that? All right. And then multivariate methods. There are different approaches to this modeling method. They all are considering how variables are correlated and how they relate to each other, but some are more difficult to apply in practice than others, especially if you're thinking of commissioning this so that it's running as part of or in conjunction with, say, a control system or a data processing system that's processing your data in real time at a plant or near real time. So I would suggest that because my personal belief is not to overwhelm a project with too much technology, that you would try for a high bang for the buck value that you might get from PCA and PLS methods first, and see what you can do with those approaches and combine them with something like a time series model to extract, in my opinion, very useful information out of a data set to the point that you can use them for process improvement. And then if you see a need to extend it to other methods, then you can certainly do that. But we're going to focus on the time series methods and on the PCA PLS approaches. Okay. All right, so let's look at this one technique at a time. The time series methods, these approaches could be cast in many mathematical forms, and the one I kind of gravitate to is the ARIMA modeling, autoregressive integrated moving average model structures. Okay, these models are parsimonious in the sense that they have very few model parameters. And when they're built properly and fitted to data in an appropriate way, they can be very useful and very informative. You could have a model for a data set like this that's an ammonia in a bioreactor. It looks like a simple data set, but it's deceptively complicated, or potentially difficult to model all of the information that's in something like this data stream. So an ARIMA model will provide that for you. And the idea here is that you want to fit something that's simple yet informative, and it's easy to work with and easy to develop. And for me, these techniques have proven to be successful over many years of applying them and use in various projects. Okay, so the model forms are not very difficult once you work the math out, and you get a model that has very few 2 or 3 model parameters that need to be estimated for this. Now, the applications of multivariate methods and the statistical modeling of groups of variables. There are 2 general approaches in this latent variable kind of framework that's part of multivariate statistics. One is PCA, which is a principal component analysis. You can think of that as a correlation analysis that can be used for fault detection, event detection, process debugging, identifying why certain changes have occurred in your process, what is going on that's different now than it used to be. These kinds of questions can be answered using the correlations that you can derive out from a PCA. And that typically works on decomposing a table of data. In this case, it's labeled X, on process values that you, like from sensors. You might combine that with lab values and just see what the correlations may reveal. Now, if you want to extend that, you can take those values and then see if they can be used to make predictions of values that are typically not measured, or at least you can measure them easily or very or cheaply or very often in a process. The PLS approach, projection to latent structures, can provide a model simultaneously of the process inputs that you're using, but also of the outputs, and then how these two relate to each other as well. And what that's good for is for developing soft sensors, but it has the ability to provide monitoring and fault detection kind of as a built-in or as a byproduct of modeling those process inputs. Okay, so the idea then is to use this structure to see if we can generate some useful models and what these models can be applied to. Okay, so the 2 examples that that you can get a good practical advantage from, we're going to show that as case studies, and hopefully you can see some of the advantages of applying these methods. For the practitioner or the person using the methods, basically, once you have the data sort of loaded and put together, what you get out of it is a systematic or repeatable method of processing your data that you can automate or have it in a semi-automated way through software. That's generally speaking a time saver. Okay, once the data are loaded into a software package for analysis. And then in terms of the plant operations, you can think about targeting operating costs and increasing efficiencies of various kinds, depending on what your data study is going to be related to. All right, so these are the kind of advantages that we're targeting with applications of these methods, and realize again that we're looking at combinations of these techniques, and that we're not advocating that you would use any one of them, any method that we're discussing here on its own, but that the methods can and should be combined with various modeling approaches to provide a desired outcome for your project. Okay. All right, so Live is going to introduce this this next case with the view on adjusting sensor data.
Okay, hello everyone. My name is Live Rieger, CEO of InControl Solutions. My job here is to introduce the project just a little bit and then mainly focus on the problem statement for Ivan's data work. Right? So the idea, as Alex had already outlined, is that we thought it might provide an easier entry for the methods if you understand what he's trying to solve. So in this example here, or in this project, we were working on quite a complex treatment plant, so wastewater treatment plant, with basically 3 completely different sections, and we were supposed to analyze the aeration control system, and we had some doubts how to properly model the hydrodynamics. Yeah, so there are different ways of doing that. So we thought about tracer experiments, but basically the budget was limited, and we thought, well, let's use online sensors. The plant is already equipped with quite a few, and we decided to basically rent much more sensors. So that was a big installation. In the end, there was little water left in the tank, so we had 1 pilot tank. So we have put that in with the idea that we, in parallel, carefully designed a measuring campaign with grab samples analyzed in the lab, and that we would not spend too much time calibrating the sensors up front. We would do that after. Right? So typically we would say, don't touch the sensors, and we have everything under control. And that was what we did. So focus really on online sensors, but we carefully designed that we have the right lab data to support a calibration after the campaign. Yeah. Next slide. So unfortunately, what came back was more than just a calibration issue, right? So not all the sensors. Basically, we had 2 tasks. One is making sure we understand the influence to all 3 sections, and then a specific task analyzing the hydrodynamics was very high resolution data. Yeah. So what came back is actually that mainly the influent measurements had not just a calibration issue, they also had a drift. And if you see the COD time series, that shift here, we realized, unfortunately, after collecting the first set of lab data, that the wrong base calibration was used here. Yeah, so we decided, let's switch, and then we thought maybe we cannot use the first part of the data set. But basically, this is what came out, right? And of course, that's a nightmare. And I thought I could do the linear correction to recalibrate the sensors myself, but well, that is above my knowledge. So we got Ivan involved to make sure we can use the data, right? So what you can see is there's plenty of lab data available, and the online data, well, doesn't fit at all. So we had to find a way to use the information in the online sensor data, so mainly on the dynamics, but remove drifts on that one shift in the COD data. Good.
All right. Okay. So let's look at the details of this, and maybe you can get some ideas from this, and how you can apply some of these time series methods for doing an analysis like this. So remember that what we're looking at here is developing a model quickly and that we want an effective model that has a few model parameters that are easy to calculate, easy to estimate, so that they can be used for correcting the data set. And in this case, the focus is on removing sensor drifts, accounting for disturbances, and compensating for various faults in the sensor data, or maybe the lab data, or both, as these things may occur. In this case, the focus was on the sensors. And then realize that that we're using detailed knowledge of the model structure that we're developing to look at developing a way to account for this. Okay, so how does this work? Like in basic terms. This is an example data set, and you saw it on a previous slide. It's basically ammonia data in a bioreactor, and this is not part of this project. It's just meant as an illustration. You look at a data set like this, and you might think, okay, well, I can clearly see that the data have a certain mean. There's a spread in the data set there, so I can find a standard deviation. That might tell me something about the operation of the reactor. But I would suggest that that you should also look at the time-based correlations that are apparent in this time series if you take a closer look at this. All right. So where do you begin? Okay. These plots here show you the explicitly what the correlation structure is in this data set. What we're plotting on the x-axis in both of these plots is the current measured value, okay, in time. And then on the y-axis, it's the previous measured value. On the top plot, it's the previous sample, and then the bottom plot, it's 2 samples ago. Okay, so as you can see, then that there's a significant, clearly visible correlation between the current measured value and the previous one. And as you go back further in time, maybe that correlation gets a little bit weaker. Okay, so what this suggests is that that you can use an ARIMA model structure, in this case with a single model parameter, to mathematically express that correlation structure. And the idea here is that you would generate a one-step ahead prediction, figure out what the difference between the predicted and the actual value is, and then minimize that to achieve a fit of the model to the data. Okay, and you can do this prediction over a horizon of whatever length. In this case, I labeled it L, but you can do a prediction horizon over many samples if you need to, and depending on the order of your model, that can be pretty effective. Okay, so the idea then is that you can have a fairly simple model structure that can represent a fairly complicated a correlation structure in a data stream like this. And in this case, it's a one-parameter model. Okay, so what does this suggest? If you now start thinking about tuning or calculating that model parameter, you might think that you have a lot of choices in how you would set this. If you use an optimizer and you were to fit that parameter so to minimize the difference between the model and the data, you would get those last two, those bottom two plots there. The red, which is the model, following the blue, which is the data, fairly closely, which means that the model can be tuned to react to that slow drift in the data, but also in the higher frequency values that are due to random jumps in the data set. However, if you detune that parameter and you move it away from the optimal setting, you start to see that the model can start to behave like a low-pass filter, which means then that selecting that model parameter for something other than say least squares optimal kind of a model might result in something that's very useful from an engineering point of view, in that it can be tuned to track the slow drift in your data, but not necessarily react to those higher frequency changes. Okay, so that's the trick here. So what can you do with that? Well, you can take a model like that and then apply it to remove drift, but retain higher frequency dynamics that may be interesting or necessary for your analysis. Okay, and then once a drift is removed, you can replace the drift with some other value that you may think is appropriate. For example, a fixed or an average value. So that's what's done here. A time series model is fitted to this, say, TSS data in the light blue there, and you can clearly see that there's an upward drift. And then those red dots, which are the lab values, they don't match up with the black dots, which are the corresponding sensor values because of that drift and that offset. So if you apply an ARIMA model, you can fit the model to the data to account for that drift, which is that black line that follows the light blue sensor values. Once you have that, you can subtract it off from each measured value and then add back the center value that you get from the lab, which basically shows you that you have a corrected sensor. So now the sensor corresponds to the lab values. It's stationary. There could be some slight drift that's still left in there, but it's generally stationary, and the lab values match up with the sampled sensor values fairly closely. Okay, so that's an easy way to do drift removal on a sensor. You can also apply that for cases like this, like in the COD time series. It's similar here in that there's a drift removal, but you can also apply this for different means and different at different portions in the data set as needed, again to achieve this stationarity that's desired for comparing a sensor to lab values. Okay, so you can take out drift, you can take out offsets, and these sorts of things based on these techniques on a fairly simple using a fairly simple method like an ARIMA structure. Okay, what also is available to you if you want to try some of these techniques is this idea of a variance adjustment. Okay, so, and again, this is the plot on the left there shows you the drift removal. So again, the blue are the data, and then that black line is in the top plot, the top left-hand plot. The blue are the data, then the black line is the time series model that's fitted, but it's detuned to act as a low pass filter for that signal, and then you can subtract that off and then add back the lab values so that the lab values can coincide with the sensor. Okay, you can make the sensor stationary, take out the drift, but what you can also do is you can recursively calculate the variance as you sort of walk through the data set. And once you've done that, you're able to adjust and correct the variance as you process the data set. So what this allows you to do then is to take out excursions in the data, like around observation around 1,000 to 1,500 on that top right-hand plot. Those values can be adjusted and corrected based on a variance estimate that you can remove from the data and then put back an appropriate variance that you think the data should follow. Okay, and you get the benefit here of reconciling the sensor fairly closely to the lab values. All right. Okay, so what this boils down to then is that I guess the main message of this case is that simple data models that account for a time dependence can be very useful, and these techniques are very robust, and they can be applied in various combinations in different modeling projects for to generate quite a bit of benefit. Okay, so Live, do you want to speak to this slide here?
Yeah, sure.
Yeah.
Interesting for me is that Ivan calls these models simple. So what we want to demonstrate here is, so we use the data Ivan corrected to feed into a mechanistic model, yeah, so a SIMBA model. And this was basically the outcome. And we wanted to demonstrate that we are actually using this process data and it works, right? So we got the results out we needed. So that combination of data-driven models for pre-processing in this case, and then feeding that into mechanistic models using other data sets to validate the model is extremely helpful. And we use these combinations all the time now, right? So that became a standard procedure for us. Okay, back to you, Ivan.
Okay, so we're looking at now maybe a bit of a discussion on that second case that we want to show you regarding the application of a multivariate statistical methods for process improvement, and Oliver is going to provide a short introduction to that. So Oliver.
Okay, thanks, Ivan. Thanks very much. This is Oliver Schra. I'm the Chief Technical Officer here at In Control Solutions, and I'm just going to give you a bit of background on this work before Ivan gets into the technical details on how we did it. And this work is this case study sort of focuses on that second method of data-driven modeling that Ivan mentioned earlier, which is the multivariate statistical approach, latent variable methods we call them, and in this case, partial least squares. And basically what we did is apply it to a pretty common problem that I think is probably an issue at a lot of wastewater treatment plants. And basically the application area is sludge dewatering. So basically sludge that's been anaerobically digested, and now you want to dewater it before you take it away from the plant. And basically, as a lot of you would know, that typically, in order to improve the dewaterability of the sludge, you might add polymer to the sludge before it goes into a centrifuge, for example, and that'll sort of improve the ability to dewater the sludge. Now, the one issue with that is that the control of the polymer dosing a lot of times I think is typically done in sort of an ad hoc manner, and it's not necessarily an automated control system. It may be just done by the operators. They'll use a certain dosage, and if they find the cake quality is going in the wrong direction, then they'll adjust the dose. This kind of thing can lead to either over or underdosing, and that will mean inconsistent cake quality. But also it'll mean increased costs potentially because you may overdose and you use more polymer than you really need to. Now, recently there have been some feedback control systems that have been introduced for dosing control with dewatering, but they do rely on buying some sensors, and usually those could be quite expensive. So this is what we're trying to show here is sort of an alternative approach to doing that, where we make use of the data that the plants typically already collect. And we want to show basically that we can use this approach to predict something that isn't measured in often enough to be able to be used for control, and then show how that we can then use that to sort of improve the polymer dosing process. So basically this kind of thing, when you don't necessarily have a good understanding of the underlying process, well, I guess what I should say is it's a good candidate for model predictive control, because it's not a system that's easily to sort of understand exactly what will happen if you change the dose by so much. It's hard to quantify. If I change the dose by 1%, how much does that affect the cake concentration? So when it's something complicated, like such as that, where you don't really have a good physical intuitive understanding of how the system responds, it can be a good candidate for what we call model predictive control. But the problem, of course, is in this case is that there aren't too many reliable mechanistic models of this, of polymer addition. There is some, physical understanding of basically how it works, but, having sort of a predictive mechanistic model of it is another thing. So the solution we came about for that is to basically use data-driven modeling techniques where we use a data-driven model to sort of model the response of the dewatering process to the polymer addition, and then we combine it with an optimizer to find the optimal polymer dose. So essentially, it's a model predictive controller. So basically, just to give you a bit of background before we get into the details, we are really focusing on, in this particular case, dewatering of digested sludge with a centrifuge. But a lot of these other technologies that are shown here for either thickening or dewatering could be good candidates for this kind of analysis. Whether you're adding polymer or not, in each of them, I would say that we don't necessarily have, very good mechanistic models of these processes, and they all, I think, would be good candidates for the approach that we're going to show here. Now, just to give you a bit of background on the scope of the work, the client on this particular case study gave us 2 sets of data for analysis. And this is probably a very typical situation that you'll see, at plants, is that you have time series data that's probably stored in your SCADA system or collected there and stored in a database, but it's collected very frequently. So in this case, it might be, a flow rate every 15 minutes. But then there's also things that, are done with grab samples, for example, and then they're analyzed in the lab, and they're kind of done, on a semi-regular basis. So they wouldn't necessarily be done at the same high frequency, that some of the other data is collected at. And so that creates a fundamental problem, actually, that I'm sure a lot of you have encountered, is you can have this huge data set, but you a lot of times have gaps because some data is collected really frequently, other data is not collected that often, and the question becomes, what were the values of the infrequently measured data, variable? What was the value in between, those measurements? So if we only measure something once every 2 weeks, we don't really know what it was, what level it was at, between those 2 measurements. So basically, this is a typical data set that you might see in this kind of a system, and we wanted to sort of provide an analysis of the data to see if we could predict the cake concentration using these routine, plant measurements, and, do it without having an additional sensor. And then we wanted to devise a method to sort of improve or change the dosing practice of polymer. And the one point I just wanted to highlight here is that with the data that's sort of shown on the right side, the operator entry data, where the operators would take this data that's, analyzed in the lab and then enter it into a spreadsheet, for example, that data, a lot of it had cake concentration measurements, but they're not collected often enough that they're really that useful for control. You're always kind of behind when you do it that way, because you may not get a measurement for a week later to reflect a change that you make today. So that's really, where this approach we're going to show next comes into play.
All right, so I can show you some details of how this study worked. Basically, as Oliver was saying, that this is based on a PLS model approach. Now, the main thing to get out of this sort of description of how this works is that the modeling method provides a model for the process for the model inputs and for the model outputs. And what this allows you to do is to apply various missing data handling techniques to measure or to account for any gaps or faults in the input data, but it also allows an optimizer to make use of the correlations that you get out of that to set reasonable values for meeting, in this case, a cake concentration. So the way this works is that the optimizer is used basically to back solve the model to achieve a certain cake concentration. And the idea here is to compare the model prediction at each step that the optimizer takes in its minimization iterations to see how close the predicted cake concentration is to the target, and then to use that to generate plant settings to actually achieve those targets. Okay, so this is often, if you're going to consult the literature on this, this is often called the model inversion problem. And basically what it does is it specifies the outputs of the model, and then it back calculates, or it sets the model inputs to achieve that desired output. And this is what the optimizer is going to do with the PLS model at each iteration that it takes. Okay, so what do the outcomes look like here? So in this case, blue is the current practice, and red is the PLS optimizer kind of a model. In this case, we looked at a couple of different scenarios. The first one is with putting a hard bound on the upper limit of the dose. We wanted to show that we can get the model to dose the polymer in a way that is always less than what the current practice is at the plant. And you can see that on the left side that the red model dosing amounts are always less than the blue ones. And then in the middle plot, you can see that that black line, that targeted cake concentration is met more often or about as often as it is with the current practice. So we can meet the targeted cake concentration, but use less polymer to do it. Okay, that's the first outcome with this. The second outcome is that when we lift that constraint and allow this model predictive kind of a control scheme to be more aggressive, it can dose more than the plant currently does, or it can make the doses more variable as needed, which is what you see on the left side. But what that results in is a very tight a meeting of the desired cake concentrations for delivering the target cake concentration. Okay, so in this case, what this suggests is that a controller can be built with this scheme in mind that is certainly tunable, and it can be set up according to the needs of the process operator. All right. So what this suggests to us is that data-driven models can indeed be used to predict cake concentration, and when you combine them with an optimizer, you can improve a polymer dosing for dewatering with a fairly high potential for cost reduction. At least that's how we see it so far. Okay, so Live is going to show you very briefly some other cases and then conclude the talk for us.
Good. So we had a hard time picking two examples. So we are already close to the end of that webinar. Just two cases. One is in our biogas work. Very important there. So that's industrial biogas systems in that specific example here. And they feed a lot of different feedstocks to their digesters. And to help with the analysis Ivan's tools proved very, very helpful. So identifying critical feedstocks, helping to reconcile data and so on. And that's just one example. So we have a couple now where we can demonstrate that data pre-processing helps a lot getting proper results out of a mechanistic model. Again, so similar to the first example, there is data pre-processing, data analytics, and that is fed into a mechanistic model. And sometimes we apply data-driven models for analysis and diagnosis to the outcome of the mechanistic models, right? So these hybrid approaches are very, very useful to us. The other one is something we do for every single project we are doing now. So we do a lot of wastewater treatment plant simulation studies. Our first step all the time now is we have developed standard tools for that, is to clean up data, augment data. Augmentation means filling the gaps you necessarily have. And then also detect pattern in the data, right? So what you want to get out at one point is you want to know what a typical dry weather data set is, or by, let's say, a week, for example. And then you also want to be able to separate dry weather from rain events or any special events, right? And that data work up front saves us a lot of time. Yeah, so we do that. Next slide, Ivan. So we do that also for our clients now, so only providing the data work and then they do the mechanistic modeling. But in general, just to summarize our experience with these combinations of modeling worlds, or these hybrid approaches, is that we save a lot of time. Yeah, so we have standardized a lot of that, and to get to a useful data set. So our rule of thumb is that you spend about 60-70% of your time of a classic simulation study on data. Yeah, so that reduces our efforts enormously, and the side effect is that the data is much, much better. Right? So it's complete because we fill the gaps with methods which go way beyond just using linear interpolation of one variable at a time. Yeah? So using these data-driven models to fill the gaps proved extremely useful. Better data translates right away to less uncertainties, lower risks, and in general better recommendations for our clients. Yeah. The second example we picked because that is a direct application of data-driven models for optimization of processes. Right, so that doesn't or didn't involve any mechanistic models. And that's also an application we do more and more. And I think the big advantage of In Control is actually that we provide both tools and combine them. Yeah. So the next topic basically is that we have standardized a lot of these things. So model building for PCA and PLS is fully automated, for example. And we have a quite powerful database behind, and that data integration part is extremely helpful, right? So you cannot do these studies in Excel, right? So you have to be aware that you need special tools to actually apply all these methods. Just a little bit on our background to finish the presentation, and that is purely the focus on Ivan's team, or the data work he and his team are doing. So we do a lot of data integration, data cleanup, and augmentation. That is the whole data pre-processing part. The analytics will come in more and more in our work. So we did a couple of projects where we focused on that, but again, so the advantage really is the combination. Process monitoring, developing these monitoring schemes is something I think we are quite advanced now. Things like fault detection, detection of events in the process, separating faults in the sensors, faults or process upsets, and then of course also process optimization studies like the second example. We develop two software products. One we call Ops Control, that is our monitoring and control platform that runs online and provides intelligence in near real time. Also does a lot of control work, so our patented ABAC SRT controller is in there in the package form. We have controller performance monitoring, we have auto-tuning in there, and so on. The second package is data control, so that is our package for offline data management and data analytics. That is quite interesting because that whole data integration part is typically a big challenge, and often that's the biggest challenge, to get all the data into one format and use a standardized data model behind to be able to easily apply all these methods and mainly automate the tasks, right? So, and our goal is, so we are very close now, so we are testing the whole procedure is that you load the data in and then you basically push a button, all the models are automatically generated, and what you get out you specify up front. But let's say for a mechanistic modeling study, you push a button and you get the data sets out you need for calibration validation and then for typical process conditions. Good. That was my part. Back to Alex.
Thank you, Yvonne. Thank you, Oliver. Thank you, Live. That is going to wrap things up for our Garbage In, Knowledge Out webinar. If any of you come up with questions or have any feedback that we didn't get to during this talk, feel free to follow up with us directly, either via email, on our website, or on our LinkedIn page. We'd also ask you to please stay tuned for future In Control webinars and webcasts. We're brainstorming the next batch, and we'll post info on LinkedIn very soon. And finally, thank you very much for sharing part of your day with us. Take care, stay safe, and we look forward to future interactions. Really nice spending time with you all. Take care.